Our next speaker will be Cari Martinez. Cari is a principal computer scientist in the Applied Machine Intelligence Department at Sandia, and she is a technical lead of a team that focuses on applied deep learning. That's all. Welcome, Cari.
Thanks, it's great to be here. Am I able to see my slides from here at all? Oh, there we go. Okay. I just saw me for a second. It's not what we need. Okay, so thanks. As mentioned, I am a researcher at Sandia National Labs, and I lead a team focused on applied deep learning research. So what that really looks like is that my team is presented with problems in Sandia's mission space, for which there is a lot of data and resources, and we are asked to try and solve those problems, which means that first we converse a lot with subject matter experts to understand the data that's available for these problems, and then we look to the literature to find what the current state of the art is, whether that's internal literature, literature from our collaborators, or that's the big tech companies that are coming up with the latest and greatest machine learning solutions to problems like we have. As identified earlier, though, actually Emily already mentioned this, when we get to real world settings and try to take things from like academic studies and apply them to the real world, there are challenges associated with it. And so in that context, the problem that we're looking to address is in terms of understanding how we can expect our machine learning models and methods that we're developing to perform in the real world. So several teams at Sandia are looking at this, and we're trying to come up with a standardized approach to assess these machine learning models. So answering questions like, does the model perform its task correctly? Will it perform well when deployed? What are the limitations? Are we communicating these things to end users? These are questions that we seek to answer. Yesterday, if you saw a talk from Mike Smith, he presented a workflow that we're working on to assess systems that have machine learning components in it. What I'll say here is that some of those steps are assumed to have been done before we get to this machine learning component analysis. So things like scoping, what are the kinds of risks that we care about, such that we can answer the question, how well does the model perform its task, and what risks exist within the scope that we care about for deployment. Another thing I'll preface this talk with is that there is no single tool or process that will capture everything that we need to know about a specific scenario. And so really part of those pre-processing steps in understanding scope involve what kind of artifacts, what kind of evidence do I need to collect to really get at and understand the risk associated with my model. So let's see, laser. Here are some steps that we've come up with that we think are an abstraction, 6 concrete steps that we can follow. It is a little more standardized, but how we actually implement those steps will vary dependent on task. And for the rest of this talk, I'll walk through all these steps. And the focus of this talk, I think it's in the program, is for the practitioner. So not only am I speaking from the position of being a machine learning developer, but also those who want to come in and assess machine learning systems. And the focus of this talk is not a comprehensive survey of all the ways we might do this. It's a curated survey of tools that we've found to be accessible, that are very easy to integrate into already developed methods and systems. And so today, the main topics that I'd like to cover are a data review, methods for evaluating models, and then finally looking into robustness. So things like uncertainty quantification, explainability, reproducibility. And one of the goals of this talk is not only to share these tools that we've identified as readily usable and useful, but also to motivate other deep learning researchers and evaluators to say that uncertainty quantification, explainability, reproducibility are not extra credit exercises. It's actually something that is useful and should be part of our daily routine. So starting with the 2 first steps of our evaluation protocol, we first would like to inspect and assess the data used for training and evaluation, and second, compare the training and evaluation data to real-world data sampled from the intended deployment domain. And here I'll just highlight 2 tools that we found to be useful so far. One is called Datasheets for Datasets, and the second is Deep Checks. So, by the way, all of these tools are open source tools. These are available to the public. And so that's another focus of the talk is it accessible for everybody? Data sheets for data sets comes from the literature. It's from a group of researchers from many institutions. I think Google, Black and AI, Microsoft, and several university partners came up with just the standardized way to describe what is the data that you're using to implement your model. So this is not a comprehensive list of all of the questions that this data sheet template provides us, but it's just to give it an example of what kinds of things we look at when we're reviewing data sets. So for example, things relevant to national lab model building for the motivation. For what purpose was the data set created? Typically in the academic literature, you might find that data sets were actually built to assess machine learning models. They're curated, they're very nice. In the real world, I'm getting data that's for science and engineering testing. It has nothing to do with the intent of making a machine learning model. So what challenges does that introduce? Let's capture that here. Second, obviously the composition, what is the data set comprised of? But I do want to highlight one of the most important things about this. Does the data set identify any subpopulations that we should think carefully about? This was already highlighted earlier today in one of the talks, or actually in the panel, the discussion that oftentimes models may not be performant in the same way for different subgroups of the population. So say, I don't know if it pick a demographic like women in STEM, like does the model perform well there? Well, I certainly hope so. But this data sheet also captures this as a point that I need to consider when I'm developing these models so that I'm remembering that there are groups that maybe I'm not associated with that I should consider when building models. And if I know that there's a chance performance will degrade for those groups, you know, maybe I shouldn't be making predictions where I don't have sufficient data that represent those groups. I won't go through the rest of these, but these are just examples, collection process, things like pre-processing, especially pre-processing, I guess, in scientific contexts. If there is sort of legacy knowledge of how data is acquired and stored, that is really important to capture. So at the end of the day, the product of this data sheet, it provides a template. It is a manual effort to fill this out, but what you're left with is a concise representation of the data in one document that describes what you use to build a model. Second on the tools that are readily usable for data review is a Python library called DeepChecks. What we found is they have a data integrity suite, they have a train test validation suite. And both of these are just, if you can see here, it might, whoops, back. It might be a little small to see, but to implement this into a Python script, it's 4 lines of code. Very low effort, and all of a sudden, all of the exploratory data analysis that I used to program by hand every time is provided to me. So I can have things that look for correlations among features, look for distribution shift among features, and not only that, it's set up as a test suite, and so automatically areas of high risk will be identified with some explanations as to what mitigations you might seek. It's a really nice set of tools. Okay, shifting to the model review. We have 2 goals associated with reviewing the model. First, review the machine learning source code. And second, independently train and evaluate the machine learning model in an environment similar, hopefully identical to the deployed system. So this is the kind of thing where ideally, when we care about deploying these models, we probably want an independent team to come in and do a peer review and actually run the model, like make sure that these metrics are reproducible, that the developers are claiming about their model. So again, this is not a comprehensive list. These are some tools that we've identified to be readily usable. I'll walk through the first 2, but I do want to highlight things like the Responsible AI Toolbox, the Adversarial Robustness Toolbox. I know these have come up actually in other talks, so I think others are familiar with these, and as well as AI fact sheets. The Responsible AI Toolbox is from Lincoln Labs, and I think that I saw in my research for this talk that there's now also a Microsoft version of this. I don't know if anyone from Lincoln Lab is here, but I'd love to understand what they think about that. And then the Adversarial Robustness Toolbox and AI fact sheets are both products from IBM, and I think AI fact sheets, I'm going to talk about model cards in a second, but that combines some of the advantages of the data sheets and the model cards that I'm going to talk about here. And if you're in the IBM infrastructure, I think there's some automation available to that. So model card, very similar to the data sheet, but for models. I won't belabor the point here. It's a manual thing where it's a checklist of things and questions to answer about your model. But the idea is that it will help you not miss things to consider as you're developing model and evaluating the model. So very similar in nature. We can see some of the factors. We're looking again at the performance for specific demographic groups when we have human-centric data. In science settings, that can also mean sort of data at sort of extreme ranges of physical behavior that you might want to consider that might be absent from your data sets. And then back to deep checks. Again, this is another example where 4 lines of code, if you have, I think this is currently limited to scikit-learn models or models that implement the functionality of scikit-learn. With 4 lines of code, you can run an evaluation suite, compare train and test performance, error analysis compared to baselines. And then what I have on the slide here is an automated assessment of a weak subpopulation and performance. So for a specific data set in the red here, I know the numbers are hard to see, but this automatically identified that a certain combination of ranges of features have poor performance from a trained model. So given a data set, a test data set, and a trained model, you can get this with these 4 lines of code, among other tests. Okay, and then the final 2 points are the most detailed. So this I would consider under the umbrella of interpreting and documenting model results. And so step 5 in our assessment process of this machine learning model is to review methods used to understand model behavior, such as explanations and uncertainty quantification. And 6 is to document those findings, anything that any risk we've identified, and recommend mitigations. And so this is a smaller subset of all the available tools. All of these are active and open areas of research, but I'd like to share just a couple of anecdotal incidents where I avoided some failure just by doing some simple things by way of some of these tools. And so we'll talk through Monte Carlo dropout in the context of deep learning uncertainty quantification. SHAP is an explainability method, post hoc explainability for black box models, and then finally reproducibility with weights and biases. First, stepping back for uncertainty, I think it's interesting to note that, well, first, disclaimer, I'm not an uncertainty quantification expert, and I think a lot of people here are, so that is not me. So I'll make that clear. But I think there are also a lot of deep learning practitioners who are not uncertainty quantification experts. And we can evidence this by looking through the literature and seeing that there are actually inconsistencies with how we represent what we mean by uncertainty. There's a lot of imprecision in the terminology. So at Sandia, there's some ongoing work under the LDRD program to sort of formalize into a common language the way that we might approach uncertainty quantification for deep learning and machine learning modeling, as well as, I need to go through this, get all the way through the slides, as well as they're proposing a formal framework such that we can evaluate the quality of these uncertainty estimates that are being proposed in the literature. So this is ongoing work. I'm excited, and I hope that I can add this to the set of tools that I can talk about as being something easy to implement so that we can understand when we have uncertainty quantification, how credible is it? So moving on to the uncertainty quantification by way of Monte Carlo dropout for neural networks. This is some work from Gal and Garamani from, I think, 2015. It was a dissertation out of Cambridge. And you know, the problem that they were trying to address is that a standard neural network, vanilla neural network, does not provide any sort of error bars. For a while, I think people thought that softmax output, if you're familiar with classification problems, can give you some sense of uncertainty. And within the training domain, sometimes that's true. But if you have some examples that are out of distribution, then softmax is not going to give you a good estimate of how uncertain the model is. And so this is an example here of the output of a softmax layer within the training domain. We get values that range from 0 to 1 for a 0-1 classifier. Outside, where we had no training examples, the solid black line represents what you get from softmax, which is that we are very confident that this is a 1. That's not actually the case, and the method proposed in the literature was to have active dropout layers during inference, and to get to introduce some stochasticity into the model so that we now get a range of softmax values, we get a distribution, and we can see that the effect is that we don't have certainty anymore around at that out of distribution sampling. So this is where the error in my ways will be presented for the rest of this talk. So we implemented some uncertainty quantification by way of dropout into an image segmentation model. So for this task at Sandia, some of the things that we do with deep learning, we automate some tedious processes. Some of that's image processing. And in the context of things like material science, we might get a CT scan of something. So that these are examples of batteries. And we might want to model based using some simulation what the performance of the expected performance in the field of batteries might be. To do that, we need to process these images. Process these images into binary examples so that we know where battery particles are and where they aren't. So one of the things that we did is we built a deep learning model. It's very good at segmentation. We can segment these automatically. And it's hard to see on the screen, but we can capture uncertainty around where we think battery particles are and aren't, for example. So great. We had some success with batteries, so we were asked to segment some other types of materials. So this is a different type of material, and I trained a model. I did this. I was given a data set with very nice labels, and instead of giving the nice labels to my neural network, I gave it this. So this is a material that has a bunch of defects in it, and I gave it a pristine example for a label, and I trained. And so then I looked at the results, and guess what? When I input this to my model, I output this as the prediction. Terrible. So looking at just the accuracy of the model, I was about to say, you know what, we don't have enough data. It just it didn't work. We need more. But because I had uncertainty implemented, I also looked at the uncertainty and saw that everywhere where there was a defect, there was a high uncertainty in the prediction. So that saved my day a little bit. So then I was, well, how is that possible? So then I looked and I saw what I did, and I actually retrained, and now we have a very nice segmenter for this particular example. But that's the point, is it didn't take a lot of effort to add dropout, to make it active during inference. It takes a couple of lines of code to get a distribution. Yeah, you have to collect a few inferences, but it saved the day, right? Okay, shifting gears to explainability. So explainability is obviously an open and active area of research. I'd like to say that this is low-hanging fruit. It's not perfect, but it's useful, I guess. So one of the methods that we have used for explainability is known as SHAP. The 1-minute version of what SHAP does is it's based on Shapley values from math, from game theory, where the goal is to attribute feature contributions for the model predictions from a deep learning model or a machine learning model generally. What SHAP is a Python package that includes model agnostic explainability implementations of these Shapley values, their approximations to them. And a thing to note is at the end of the day, these are linear approximations to complex, often complex nonlinear mappings. So we do anticipate we'll have some error with the fidelity to some of these explanations, of these explanations to the model behavior, but it's enough to be useful. So to motivate how we've used this and how this saved us from yet other modeling errors, I'll motivate this with a project that we have ongoing at Sandia. So this is a collaboration with the Department of Veterans Affairs and several other DOE labs, where we seek to identify risk for US veterans given health records of adverse health outcomes. And so we're building models that take 5 years of longitudinal health records and attempt to predict the likelihood of an adverse event. In particular, one of the models that we're building is to try to predict the likelihood of a suicide attempt or risk for a suicide attempt given longitudinal health records. And so in aggregate, we build a model. We are predictive with that model, but we'd like to understand and provide clinicians, a reason for why a patient is identified to have high risk. And so I know these are probably really hard to read, but there are several features here. This was in our final model that clinicians have identified, and it increases some amount of trust in the model to say, yes, a history of mental health disorders is certainly something that we would see to correlate with things like a suicide attempt. What I don't have on the slide here, because we fixed it, was that we had identified a feature to have high importance that was associated with some date of data collection, because we didn't get it out of the data before we trained the model. So just having this SHAP capability, again, it's a library call, it's a couple of lines of code. I'm not claiming that this is the perfect explanation. I don't think it answers all of the questions. I think there are lots of issues with correlated features, but it was enough to say, hey, we should not be making predictions based on dates. So we removed it, and now we have a more credible model, and we looked through all these to make sure that things made sense. Finally, the last tool that I would like to share is the weights and biases. This has come up actually in other talks, so I think that we might be on the right track in using this kind of tool. What it makes available to researchers is experiment tracking. So we have model and data versioning. We can track training and evaluation metrics. It has options for hyperparameter tuning. With certain licenses, you can share results within an organization. You have interactive reports. Again, this is the amount of code it takes just to get started tracking some of the metrics during training. And another thing that I find valuable just as a developer is that I might not always be the best at committing to Git every time I make a change to code. There's an option in this that allows you to track exactly what code you ran to perform the experiment, and it just stores it there. So if I ever need to reproduce that, it's there, and I don't have to rely on myself to remember to commit everything. So I think it's great. I don't work for any of these companies, but this one might be my favorite tool because it saves me from me. Yeah, so my conclusion is a simple one. Machine learning developers can implement a few lines of code to reduce some of the machine learning deployment risks. And so with that, I'll take questions and or recommendations for tools that I should be using or sharing with others. Thank you.
All right, I'm going to start with some questions online first. Can you comment on how you are verifying the validity of your uncertainty quantification? Many of the methods are finicky with respect to validity, and we've found forecast intervals that are often fairly different from the nominal, and the Gale 2016 paper is the Monte Carlo droplet is one of the methods that we've examined.
Yeah, that's a good question. And that points to the ongoing research at Sandia that I'm hoping to leverage to answer exactly that. So they're coming up with a set of metrics as well as research into which of the methods are approximates of one another and can be associated to pare down the list of methods that we should be using that are slightly more credible. In terms of the projects that we work on, we have various ways of validating it. It's project dependent.
Another question. Oh, actually, never mind. That's not really a question. That's more of a statement there. Okay, isn't UQ meant to be used for validating models rather than the other way around?
Rather than using, sorry, can you say that again?
Isn't UQ meant to be used for validating models rather than the other way around?
Rather than models validating UQ. I think that that's true. I don't know what we're referring to in terms of the model that I am assessing or I am asserting would validate UQ. I think there are metrics that we can use to validate the quality of UQ, but I'm not sure what you're referring to with that question.
All right, thank you.
But that's a fair statement, and I agree.
Okay, questions in the room.
Hi, thank you. So you gave these nice plots on uncertainty quantification for the segmentation. And my question is, does this apply to only computer vision? Or can I use something like tabular data and do dropout? Or even something like reinforcement learning? Because that's kind of the scary stuff, right? Am I in the domain or not? So my question is, regarding the method, how applicable is it outside of CV?
Thanks. Yeah, I certainly think it's applicable, but to the comment that we just had, I think that there are issues with all of these methods, and so taken with a grain of salt. But at the face value, we can, if you have a deep learning model, you can introduce dropout at inference time and get a distribution of values. Is it calibrated? Probably not, and I think not by default. And I think there's some work to be done. There are calibration methods you can use, but certainly for tabular data, I personally haven't used it for reinforcement learning. I'm not sure. I would have to look into the literature, but there's nothing to stop you from introducing that randomness and generating a distribution and then following up with some calibration. How good is it? I don't know. Yeah.
Thanks. Hey, thanks for your talk. So I know that there's a bunch of experiment tracking tools out there, weights and biases, and a whole slew of others. So I'm just wondering how you chose weights and biases, and just to shorten my search.
Yeah, sure. I might have trouble answering that because we did have a team of people who took the time to look at a set of tools, and I don't even know which ones they were off the top of my head. I think that the ease of implementation was certainly one thing. So the couple of lines of code to track things was a thing. Could it be on-prem was another consideration for a place like Sandia. And you can do that. I think there are licensing agreements that are necessary. And I think the hyperparameter tuning was another thing. So they had a list of criteria, and I forget what all of them were, but I know on-prem and just ease of not disrupting an already sort of working workflow was part of it.
Any other questions? All right, then let's thank our speaker one last time.